Hi Year 11, it's back to virtual me. I'm sorry I'm not there with you again. But today we're going to take a little break from our elements, mixtures and compounds topic. As I said to you on Wednesday, the next part of that topic involves a bit of practical work, and it makes more sense to go on with this new topic rather than continue on with that one. So we're taking a break from that topic and moving on to this area of atomic structure today. In the last topic, we talked a lot about atoms, but now we're going to have a closer look at atoms, what they really are, what they're made up of, how they're arranged, and so on. So if you have a look down your first page of your booklet there, you can see the specification for this topic. So these are all the things that we need to learn in this topic, and we're going to be focusing on the first few today. So moving on to your second page, we're going to remind ourselves of what an element is and what an atom is to set this topic in context. So what did we say that an element was? Can you remember the definition of it? An element is a substance which... See if you can think what the rest of the sentence is. In the last topic, we said that an element is a substance that consists of only one type of atom. Okay, and then we said it cannot be broken down into anything simpler. Okay, make sure you fill that into your notes. If you remember back to the last topic, we can represent elements using particle diagrams like this. You can see that there are only pink atoms, and so there's only one type of atom in this particle diagram, therefore it is an element. So in our particle diagrams, we only ever see atoms of one colour or one type of shading, showing that there is only one type of atom in an element. So what is an atom then? Can you remember the definition of an atom? This is a little bit more of a tricky one, but an atom is the simplest particle of an element that can exist on its own in a stable environment. Okay, make sure that's written into your notes. As I said, that's a little bit of a tricky definition. It doesn't really make much sense on first reading of it. But in a minute, when you've got that definition down, we'll have another look at the particle diagram to explain this definition of an atom. So once again, it's the simplest particle of an element that can exist on its own in a stable environment. So again, this is a particle diagram of an element. And what is it made up of? Well, it's made up of these pink circles. And we have talked about already that these pink circles represent atoms. So thinking back to our definition of an atom being the simplest particle of an element that can exist on its own in a stable environment. Basically what it means is if I was to break down this element to the smallest particle that made it up that could exist on its own in a stable environment, I would be left with this little atom. So I'm breaking this element right down until the smallest particle that can make it up. And this pink little atom is the smallest thing that I could get. To put that into context, consider a full stop. So we've got a sentence at the top of our slide here, and let's zoom in on it to see that full stop. So the average full stop that you would put at the end of a sentence on your page contains 78.6 billion atoms. That means in this tiny full stop, and the full stop you write on your page, there is 78.6 billion atoms in that. So atoms are really, really tiny, but they are what makes up absolutely everything in this world. So let's have a closer look at an atom and its structure. Scientists have done a lot of study of the structure of an atom. And we know that atoms are made up of 3 subatomic particles. So for every atom, there are 3 different particles within that atom. And they are called protons, neutrons, and electrons. So let's have a look at what protons, neutrons, and electrons are. Well, in the structure of an atom, you have what we call a nucleus. And I'm drawing that nucleus now. The nucleus is at the very centre of the atom, and the nucleus contains the protons and the neutrons. But we have one other subatomic particle, and that's our electrons. Now, our electrons don't live in the nucleus with the neutrons and protons. They live in shells that surround the nucleus. You can see one of the shells has been drawn here, the circle that runs around the outside of the atom. And you can see that we have 2 black dots in that shell, and those black dots represent electrons. So I have 2 electrons that are in that shell. What happens with the electrons is that they're not still, they're moving round and round the shells. So we have our protons and our neutrons in the nucleus of the atom, and we have electrons in shells that orbit the nucleus. Orbit just means that they move around in circles around the nucleus, a bit like the Earth orbits the Sun. Electrons orbit the nucleus in shells. Here's another diagram of the structure of an atom. You can see that it's quite similar, but we just have different colours representing our different subatomic particles, so it's perhaps easier to see. So again, you can see that central area contains our protons and our neutrons, our red and our yellow particles. And you can see a circle's been drawn around them to where the nucleus is. And so we could colour that in. The nucleus is this area here that contains the protons and the neutrons. Okay, and you can see our electrons don't live in that nucleus, but they are in shells that surround the nucleus. This time we have 2 shells because we have 4 electrons. And we'll talk a bit later about how we know how to arrange our electrons in the shells. But you can see it's not just one shell that an atom can have. An atom can have up to 7 shells. In this case, there are 2. So if you were asked in an exam how to describe the general structure of an atom, here would be the sort of answer that the exam would be looking for. You would say that an atom has a central positively charged nucleus. We'll talk about where that charge comes from in a second, containing protons and neutrons surrounded by orbiting electrons in shells. So in your answer, you're explaining that we have 3 different types of subatomic particles. We've got our protons, our neutrons, and our electrons. And you're explaining about where each of these subatomic particles is located. The protons and neutrons in the nucleus, and the electrons in the shells. And that's something that you need to learn. Looking on down page 2, we have a table here to fill in that gives a summary of the charge, the mass, and the location of each of the three subatomic particles, the protons, the neutrons, and the electrons in the atom. We can already start to fill in this table with what we know already. So let's have a closer look at this table. Okay, we can fill in the very right-hand column of this table already, because we know the location of the protons, the neutrons, and the electrons in the atom. So where's the proton found? The proton's found in the nucleus. Where's the neutron found? Well, the neutron is found again with the proton in the nucleus. This is a good point to point out the difference in the spelling between neutron and nucleus. Neutron is spelt Neutron, but nucleus doesn't have that U at the start of it. It's spelt Nucleus. So just be careful about the spelling of that. Okay, and where is the electron found? The electron's not found in the nucleus, but is found in the shells. So fill in the table in your notes with the information that we already know. So try and get that into your head, that the protons and neutrons are in the nucleus and the electrons are in the shell. So what do we mean by the relative charge and the relative mass? Well, I want to start off, first of all, with the relative mass. If you have a look on down in your notes, you'll see that it's explained that actually the actual mass of a proton is 1.6725 times 10 to the minus 27 kilograms. So that is really, 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 really light. There's no way we could ever measure that. We could never weigh that on a set of scales that we own. And we could never work with those sorts of numbers. They would just be really, really small. So what we do instead is we give a proton a relative mass of 1. So we say that compared to the other subatomic particles, a proton has a relative mass of 1. And it's the same for a neutron. Protons and neutrons have roughly the same mass. There's a very, very tiny, tiny difference on that tiny scale. So we say that a neutron has a relative mass of 1 as well. So for every proton we have, it has a mass of 1. So if we had 3 protons, it would have a mass of 3. And if we had 6 protons, it would have a mass of 6, and so on. Electrons are a little bit different in that their mass is even more light than a proton or a neutron. Compared to protons and neutrons, we say that an electron has a relative mass of 1 over 1,840. Now that seems like a very random number, but it is a number that you need to know, a fraction that you need to know. You need to know that a proton has a relative mass of 1, a neutron has a relative mass of 1, and an electron has a relative mass of 1 over 1,840. What that means is that when we're comparing the mass of an electron and a proton, say, a proton has a mass that is 2,000 times more than the mass of an electron. Okay, so what about the relative charge now? Again, the exact charge, and you've just come from physics, so this would probably make more sense to you than me, but the actual charge of a proton is really, really small. But again, we use relative charges to compare the different subatomic particles because those values are so, so small. So we know that a proton carries a positive charge. And so we just use it for comparison's sake. We say that a proton has a relative charge of +1. Okay? Neutrons don't have a charge, and so we say their relative charge is 0. And finally, an electron is negatively charged, and it's the same magnitude of charge as a proton, but just negative instead of positive. And so we say it has a relative charge of -1. So that's a proton is positive, so it has a relative charge of +1. Neutrons don't have a charge, so their relative charge is 0. And an electron is negatively charged, and so we say its relative charge is -1. So that explains a little bit more about our definition. If we go back up to that here, we said that an atom, the structure of an atom is a central positively charged nucleus. And it's positively charged because if we go back up to our diagram of the structure of an atom, we can see that our nucleus contains protons and neutrons. So if protons are positively charged and neutrons have no charge overall, then we can see that our nucleus is going to have a positive charge because each of our protons carries a charge of +1. So if we had, in this example, we have 2 protons in the nucleus. That means overall the nucleus is going to have a charge of +2. This table down at the bottom of the relative charges, masses and the location of the different subatomic particles is so important. It comes up in exams all the time for you to recall the relative charge, the relative mass and where these subatomic particles are. So learn this table off exactly as it is. The columns may be switched around, but do learn the values in the table. And it's really important that you learn them exactly. So for example, a lot of people would lose marks for silly things. For example, we know that the relative charge of a proton is +1, but sometimes people just write that the relative charge of a proton is 1. And that is wrong. It has to be written as +1. Another common mistake would be in the relative mass of an electron. So as I emphasised, the relative mass is not completely insignificant. It is 1 over 1,840. But sometimes people write the mass of an electron as just equal to 0. And again, that is wrong. So those are some of the common mistakes. And those common mistakes are outlined in your notes at the top of page 3. Those are 3 common mistakes there for you to look at. So make sure you learn that table and learn it exactly the way it is. Okay, for the rest of today, you're going to need your periodic table. And for this topic, you need to use your periodic table a lot. So take out your periodic table and have it open in front of you. Last week we mentioned how all of our elements in the periodic table have a name but also have a symbol, and you did some work on converting between the two of those. But let's zoom in on a couple of elements. So let's zoom in on lithium and beryllium up at the top here. So you may have noticed that for every element we have its name, we have its symbol. But we also have 2 numbers up at the top. We have a number here, and then we have a number here. And you may have wondered what those numbers were about. Well, they give us some information about the structure of the atom, which we will use now. The number at the bottom, the smaller number, is what we call the atomic number. And what the atomic number represents is the number of protons in an atom. Okay, so if I want to know how many protons I have in an atom of beryllium, I look at its atomic number. Then what about the top number? The top number is bigger. And the top number is what we call the mass number. And what does that mean? Well, that is the total number of protons and neutrons. Okay, so The bottom number, the smaller number, is the atomic number, which is the number of protons in an atom. And then the top number, which is the bigger number, is the mass number, which is the total number of protons and neutrons. Okay, so in beryllium, our atomic number is 4. That means for beryllium, our number of protons, if we represent that by P, number of protons is equal to 4. Okay, then what if we wanted to work out the number of neutrons in beryllium? Well, if the mass number is the total number of protons and neutrons, so if the mass number is the total number of protons and neutrons, and we know we have 4 protons, then to work out the number of neutrons, we take the mass number and we minus the number of protons that we have, which is 4. So 9 take away 4 is 5. Okay, so if you think about it now, our mass number is the total number of protons and neutrons. So we'll just double check that we have the right answer here. So our mass number should equal 4 plus 5, or protons plus our neutrons, which is equal to 9. And that's equal to our mass number of beryllium. So that means in every atom of beryllium, we have 4 protons and 5 neutrons. Let's now take the example of magnesium below it. Okay, so for magnesium we want to first look at our atomic number. And our atomic number we can see here is 12. So that's our atomic number. If we remember, the atomic number is equal to the number of protons in an atom. So the atomic number is equal to 12. What about for its mass number? Its mass number is 24. Okay, so let's have a think about how many protons and how many neutrons we have here. Well, we said that our atomic number is equal to the number of protons. So our number of protons is equal to 12. And then we said our mass number is equal to the total number of protons and neutrons. So if I know I have 12 protons, my number of neutrons is 24 minus 12 equals 12. And I can check that by adding my number of protons and neutrons, and I should get equal to my mass number. So if I do 12 plus 12, that's equal to 24, which is the same as my mass number as given in the periodic table. So that's how you work out the number of protons and the number of neutrons. And I should say at this stage that it's the atomic number that gives an element its identity. So each and every element in the periodic table has an atomic number. So if you look at the periodic table as a whole, you can see that our periodic table is arranged in increasing atomic number. Now, it wasn't always like that. It used to be organised in order of increasing atomic mass. And we'll talk about that a bit in our next topic. But you can see, and you might not see me underlining this, it's very, very tiny. But you can see, have a look at the periodic table. As we read across the rows, our atomic number is the bottom number. So for hydrogen, it's 1. Helium, it's 2. Then we go to the next row. Lithium, it's 4. Lithium, it's 3. Beryllium, it's 4. Boron, it's 5. Carbon, it's 6. Nitrogen, 7. Oxygen is 8. Fluorine's 9. Neon is 10. So you can see that it goes up in order of increasing atomic number. And as I said, that's what gives an element its identity. So if we zoom in on the other side here, we've got boron and aluminium. So boron, its atomic number is 5, and that means it has 5 protons in its nucleus. And that number will never change. We can change the number of neutrons, which we'll talk about next week, but we can never change the number of protons. So if you know the number of protons in an element, in an atom, then you will know what element it is, because that can never change. So say, for example, you were given a question, it said, the number of protons in an atom is 13. So you would look at your periodic table and find out which element has an atomic number of 13. And for that case, it's aluminium. And so your answer would be aluminium. Now let's think we had a third subatomic particle, and that was our electrons. We haven't talked about how we can work out the number of electrons. Well, if you remember back to our table of relative charge, what charge did we say protons had? Protons have positive charge. So I'll write up here, protons are +1. And what did we say our electrons have? Electrons equals -1. In an atom, the charge of the overall atom has to be 0. So that means the charge from our protons needs to cancel out the charge from our electrons. And the only way to do that is to have equal number of protons and neutrons. So let's take the example of aluminium. So aluminium has an atomic number of 13, which means that our number of protons equals 13. That means the charge from the protons is equal to 13 times +1, which is obviously equal to +13. That means in order to cancel out that positive charge, the charge from the electrons equals 13 times -1 equals -13. Okay, so in order to get a charge of -13, I obviously need 13 electrons. So what we find in an atom is the number of protons is always equal to the number of electrons. So why aren't the neutrons involved in this? Well, if you think back to our table of relative charge, neutrons have an overall charge of 0. So they aren't involved in this. Okay, so now what we can do is we can work out the number of protons and the number of electrons and the number of neutrons in an atom. So if I rub out this all, and then we will work out the number of protons, electrons and neutrons in an atom of aluminium. So our atomic number is 13, so our number of protons is 13. And we have just learned that in order to get our number of electrons, well, they're equal to the number of protons, so that is 13 also. And then try to think, how do we work out our number of neutrons? Well, we said that our mass number is the total number of protons and neutrons, so the number of neutrons is going to be 27 minus 13 equals 14. So in an atom of aluminium, I have 13 protons, 13 electrons, and 14 neutrons. So in summary, the number of protons in an atom is equal to the atomic number. The number of protons equals the atomic number. I want to work out my number of electrons. Well, that's equal to the number of protons, which is equal to the atomic number. So the number of electrons is equal to the atomic number also. And then our number of neutrons we need to do a small calculation for. It's always going to be the mass number take away your atomic number. Sometimes people think of working out our number of neutrons as the big number minus the small number. Because if you think about it, the mass number gives us the total number of protons and neutrons. So let's summarise all of that in your notes on page 3. So have a look at this little box. It asks us to define what the atomic number is and what the mass number is. Well, we said that the atomic number is the number of protons in an atom. Okay, the atomic number for any atom, whether it's beryllium, sodium, lithium, carbon, oxygen, it's the number of protons in an atom. And then the mass number is the total number of protons and neutrons in an atom. Now you'll notice after the word atomic number, there's the letter Z in brackets. And after the mass number, there's the letter A in brackets. Now, these are numbers we use to represent the atomic number and the mass number. And it seems a bit strange. It would seem to make more sense to have the atomic number as A and the mass number as Z. But that's the way it is. And so you can see down below here, and we've got the general format of what is written in our periodic table. So if you imagine this to be any element, E is not an element in the periodic table, but imagine it to represent the symbol of any element. So say for example it was magnesium we looked at, that E would equal to Mg. Okay, and our Z number, which is our atomic number, is always at the bottom. Okay, so that is our atomic number. And A is the mass number, so the top number is the mass number. The mass number is always going to be bigger because it has the total number of protons and neutrons. And that comes from the fact, from looking again at your table of summary of your relative masses and charge, protons and neutrons have a relative mass of 1. And electrons have a relative mass of 1 over 1,840. So when we're looking at the mass number of our atom, we just ignore the electrons because their mass is so small compared to a proton and a neutron that it doesn't really affect the mass enough to count it. Below that on page 3 you have a summary of how you work out the number of protons, how you work out the number of electrons, and how you work out the number of neutrons. And it may be easier to do it in the order that we did it on the previous slide, and that would be to work out your number of protons, your number of electrons, which is equal to your number of protons, and then your number of number of neutrons. And you can see that that spells out the word pen. Okay, so let's have a look at one last example here, and that's the example of sodium. And sodium has the symbol of Na. Okay, so to work out our number of protons, we need to look at our atomic number. Atomic number is 11, so the number of protons is 11. Our number of electrons needs to be the same as the number of protons, and so they are also 11. And our mass number is 23, and that gives us the total of our protons and our neutrons. So the number of neutrons is going to be 23 minus 11, which equals 12. Okay, and that's summarised in the table for you. What that really means is I can now draw the structure of an atom of sodium. So I know that I have 11 protons. And think about it, where do the protons live? The protons live in the nucleus. And so I can draw out 11 protons in the centre of the atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you might want to draw this out on a spare page in your notebook to help you see it. And then what about the number of neutrons? Well, I have 12 neutrons and they also live in the nucleus. So in amongst the protons, I can draw 12 neutrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so they all live in the nucleus of the atom. And then what about the electrons? Well, they live in shells. And we'll talk a bit about how they are arranged. But in the first shell, there's always 2 electrons. So I'm going to represent them with an X. Okay, but we have a total of 11. So the next shell can hold up to 8. So now I've got 10 in my shells so far, but I have 11 in total, so I need one last shell, and that gives me 11 electrons. So that drawing there is the structure of an atom of sodium, and you may well be asked to draw this in an exam. And the last thing you would need to do, just like with our apparatus, is to label it. So we'll get our key at the side here. So the pink dot we said represents a proton. The green X represents an electron, and the blue dot represents a neutron. And it's really important that you label these so that the examiner knows what you're representing by what circle. Now obviously you won't use colours in your exams, so what you'll do is you will use, say, a white circle for a proton and a coloured black circle to equal a neutron, and then an X to equal an electron. And that's how you'll differentiate between them in an exam. Okay, turn over to page 4 in your notes and you'll see there's a table for you to fill out with the total number of protons, total number of neutrons, the total number of electrons in each of these elements. So take some time to fill that out now, remembering that the number of protons equals the atomic number. The number of electrons is also equal to the atomic number. And the number of neutrons is equal to the mass number minus the atomic number. So take some time to complete that and pause this video while you do. Okay, now take a new page in your notebook and take the title of Atomic Structure. So we're working on Unit 1.5, Atomic Structure. I want you to spend some time working out the number of protons, the number of electrons, and the number of neutrons in these 20 atoms. Now, I know that's a lot, but it's really important that we get the hang of how to do this so that it's second nature when you come to an exam. So what I want you to do is, so the first example is calcium. So write number 1 is calcium. And in your notebook, you'll then write the symbol of calcium, which is Ca. And beside it, I don't have any room beside it, but beside it, write number of protons equals, and then look to your periodic table. The atomic number is 20, so the number of protons is 20. The number of electrons is equal to the number of protons, so that's also equal to 20. And then our number of neutrons is going to equal our mass number, which is 40. Take away our atomic number, which is 20, which equals 20. So in an atom of calcium, we have the same number of protons, electrons and neutrons, but make sure you write your working out for the number of neutrons so that when you come to look back, you know how you got to that number. So have a go at completing those 20 questions on the number of protons, electrons and neutrons in these atoms. And again, pause this video while you do this. Okay, what we want to do now is go back to our notes and turn to page 5. I just want to skip out the concept of isotopes for now and look at the idea of electronic structure or configuration at this point. We'll come back to isotopes. Now, the electronic structure or configuration, these two terms can be used interchangeably. They mean exactly the same thing. And what it really means is the arrangement of the electrons in the shells of an atom. So if you remember when I was drawing the structure of sodium, I arranged the electrons in shells, and I did that in a particular way. And all the atoms follow the same 5 rules, and the 5 rules are outlined here. First of all, that our shells are at increasing distance away from the nucleus. The next few rules are for how the shells fill up, and that is that the first shell can take a maximum of 2 electrons. The second and third shell can hold a maximum of 8 electrons. And then finally that the lowest shell, so the shell closest to the nucleus, must fill before the second shell, and then the second shell must fill before we start filling the third shell. And the last rule is about how the electrons pair up. But all of these rules are easier looked at with an example. So turn over to page 6 with me now. So page number 6 gives you the electronic structure of nitrogen and sodium. I'm going to take you through the example of nitrogen, but I'm going to work on a separate slide to build up to that. Okay, so the first thing we need to do in any example of working out the electronic structure of an atom is to work out how many electrons we have so that we know how many electrons we're trying to put in the various shells. And so to do that, I need to look at my periodic table. So the symbol of nitrogen, find it on your periodic table. It looks like this. Okay, so how do we know our number of electrons? Well, it's the same as the number of protons, which is equal to the atomic number. So I have 7 electrons. Okay, so I'm going to need to put 7 electrons in my shell. What we'll do for now is for our nucleus, we'll just draw a circle and write the symbol of the element in that circle. So for nitrogen, that's N. So that's representing our nucleus for now. So N is for nitrogen, not for nucleus. Okay, so for our first rule said that our shells are at an increasing distance from the nucleus. So the first shell is going to be right next to the nucleus. Okay, our second rule then said that the first shell can hold a maximum of 2 electrons. Okay, so we're going to represent electrons by X's again. And so there are 2 electrons in the first shell, and they sit together in the first shell. Okay, but I need 7 electrons. And so I need to move to my next shell because my first shell has the maximum amount it can fill. Okay, our third rule says that the second and the third shell can hold up to 8 electrons. Okay, so I'm going to put my next electrons into my next shell. So at the minute I've used up 2, so I still need to put 5 electrons in the next shells. Okay, how we arrange them in the second shell is a little bit different. What we do is we put them at north, east, south and west, and then if they need to pair up, then they do that in the second round. And so my 5th electron is going to pair up with the first one at north. So I can't just put electrons here or here. They have to go at north, east, south and west. So I'll rub those ones out. Okay, so count up your number of electrons. We have 2 in the first shell. 1, 2, and then 1, 2, 3, 4, 5 in the second shell, and so we have our total of 7 electrons. So that is our electronic structure of nitrogen. So following our rules, our shells are at increasing distance from the nucleus. The first shell can hold 2, the second shell can hold up to 8, but we only had 5 to fill it with anyway. And the last rule, that the electrons pair up, but only when they have to. So we put them at north, east, south and west first, and then we start to pair them up. The next example in your notes is that of sodium. So again, first step is work out how many electrons you have. And again, that's always going to be equal to the atomic number, which is 11 in this case. So I have 11 electrons. And I'm just representing that by E minus, because E for electron, and then minus because electrons carry a negative charge. Okay, so first things first, we're going to draw our nucleus. And this time our symbol is Na. So we'll draw a symbol of Na with a circle around it to represent the nucleus. Okay, we've got our first shell. And how many electrons can the first shell take? It can take 2, and they sit together because there's only one place for them to be in the first shell. The next shell can hold up to 8, but remember they only pair up when they have to. So I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, and you should fill it up like that to get you in the practice of only pairing them up when they have to. So count up your electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 at the minute. And so I still need 1 more electron. So I need to go to my next shell. So draw another shell and pop an electron in there. And there's our total of 11 electrons. So that is your electronic structure of sodium. Now what we'll do in this case is we can also write it in a written numerical form. And how we do that is simply we write the number of electrons in the first shell, so in this case it's 2. Then we write a comma and then write how many electrons we have in the second shell. So in this case we have 8. And another comma and then write how many electrons we have in the next shell, which in this case is 1. So that's our electronic structure in numerical form as well. Okay, so going back to your notes on page 6, I want you to draw in the electronic structure, the electronic configuration of the 4 examples there. There's 2 on page 6 and then 2 on page 7. So I'll do the first one with you here. Okay, the first example is for beryllium, so you need to look at your periodic table and find out how many electrons you have. So beryllium looks like this on the periodic table. Its mass number is 9 and its atomic number is 4. So we always look at the atomic number for a number of electrons. So in this case, beryllium, it has 4 electrons. Okay, so again, first step, draw my nucleus. which is, my symbol is Be. And then my first shell can take up to 2 electrons. So I've got 1, 2, and remember they sit together on the first shell. And then I move to my second shell, and I need to have a total of 4 electrons, so I only have 2 more to place. But this time I don't place them together. Remember, we put them at north, east, south and west first. So I'm going to put 1 here and then 1 here. And that's me finished because I have my 4 electrons. So just be really careful always to use your atomic number and not your mass number. Some people make the mistake of using the mass number as the number of electrons, but then you're going to have far too many electrons. Okay, we can also write this in the written form. Remember, we do that by writing the number of electrons in the first shell, then a comma, and then the number of electrons in the second shell. So that's our electronic configuration of beryllium is 2, 2. Okay, so try that for the example of fluorine, and then for the example of silicon and calcium on the next page. And pause this video while you do that. Okay, so let's check your answers for those now. So for fluorine appears in the periodic table as 19F9. So our number of electrons is equal to our atomic number, in this case is 9 electrons. And so you should draw your nucleus in first, with the symbol of F for fluorine. In the first shell, we have 2 electrons. So that means we need to fill 7 more in the second shell, and it can hold up to 8. So they're all going to go in the next shell. 1, 2, 3, 4, 5, 6, 7. And so the written form of our electronic configuration is 2, 7. So that's what your electronic structure should look like for fluorine. So make sure you check that that's right. Okay, now for silicon. Silicon looks like this on the periodic table. Its mass number is 28 and its atomic number is 14. So we get our number of electrons from the atomic number. So I have 14 electrons. Again, first things first, draw your nucleus in. Then in my first shell, how many electrons do I have? I have 2. My next shell can hold up to 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. So count up how many electrons I have so far. I have 2 in the first shell, 8 in the second shell, so that's 10, so I still need 4 more. And my next shell can hold up to 8 as well, so that's 1, 2, 3, 4. So that's what your electronic configuration of silicon should look like. The outer shell should have 4 unpaired electrons at north, east, south and west. And again, my written form of my electronic configuration is going to be 2, 8, 4. And then lastly, calcium has the symbol of Ca. So we can draw our nucleus there. And in our periodic table, it has a mass number of 40, an atomic number of 20. And so that means my number of electrons is 20. I'm actually going to rub this out, so we might need it a bit bigger. So for calcium, in my first shell, as always, I can only have 2. So I still have 18 to go. Second shell can hold up to 8. And again, they only pair up when they have to, so let's do 1, 2, 3, 4, 5, 6, 7, 8. So now I have 10 electrons. So I'm going to need 10 more. Second shell can hold up to 8 as well. So I write them as 1, 2, 3, 4, 5, 6, 7, 8. So that's now 18 electrons I'm up at, 2 in my first shell, 8 in my next shell, 8 in my third shell. And so in my last shell, I need 2 more. And again, they only pair up when they have to, so I put 1 at north and then 1 at east. And so my written form of my electronic configuration this time is going to be 2, 8, 8, 2. If you have time, now take a new page in your notebook and let's just do a little bit more practice at drawing out the electronic configuration and the electronic structure of our different atoms. So in your notebook, take a title of electronic structure. And I want you to draw out the electronic structure of these 7 elements in your notebook. So I want you to draw out your circle arrangement with the arrangement of the electrons, and then I also want you to write the electronic configuration beside that in written form. So for example, with carbon, you'll end up with an electronic configuration of 2, 4. So write that beside your electronic structure when you're finished. So have a go at drawing the electronic structure of carbon, neon, hydrogen, potassium, phosphorus, oxygen and chlorine. For your exam, you only need to be able to draw the first 20 elements. So that's everything from hydrogen to calcium, and that's the biggest atom that you'll have to draw is calcium. So have a go at practicing these ones now. And pause this video while you do that. And now if you still have time, if you turn to the questions at the back of the booklet on page 10, and you can now answer question 1, question 2, question 3, question 4, question 5, not question 6 or 7, question 8, and question 9. So that's questions 1 to 9, but not question 6 or 7. So if you have time, complete those questions now.